Good morning. In the previous class, I have discussed about the phonon and the qualitative description of phonon spectrum. Now, in this particular class, I am going to discuss about the specific heat of solid. So, let us start specific heat of solids. Now, as we know that the phonon is basically the vibration of lattice when some atomic arrangement are there in a particular lattice, and we know that the solid is basically the periodic the arrangement of lattice point, or rather I can say the arrangement of atom or molecules in crystal. It is this arrangement is rather periodic, and there exists some force between any two arbitrary atom or any two arbitrary molecule that present in a particular solid or the crystal. Now, as we know there, the positions of those atoms, these are constrained by some force in between them. Either they are one dimensional or they are two dimensional, three dimensional generalization. So there exists some kind of intermolecular or interatomic force between which is a constraint of this particular solid, or I can say the which is kept the solid in its intact form. Now, if as I mentioned earlier, in case of diatomic or monatomic lattice vibration, we know that if this system is subjected to a thermal agitation, what happens? These molecules or the atom, they are undergoing some kind of vibration. Okay, and those vibration are basically thermal vibration, and due to this thermal agitation, even the temperature is very low or the temperature is at room temperature, there exists finite amount of energy associated with this vibration, this kind of vibration. And if we go through the further beyond, further lower the temperature, then we know that at least there exists some 0 point energy. Okay, so there exists some 0 point energy. So as a result, I can say that these atoms are basically going to harmonic oscillation, even they are existed in either very low temperature or should I say very small temperature. Now, this vibration is basically independent of each other, because if one atom is set into vibration, they are not influenced by this other atomic vibration, but they are going to couple vibration in case of diatomic lattice or monatomic lattice. But those vibrations which undergoing simple harmonic motion, these vibrations are basically independent vibration. So this independent harmonic oscillator, which are in which the system is vibrating, as a result, this effect into the specific heat of solid or the energy of the particular system at any specific temperature. Now, a specific heat is basically the what should I say, the variation of this kind of energy, or rather I can say internal energy, in with respect to temperature. So as this system is undergoing into the simple harmonic motion, it largely affect into the internal energy of the specific system. So as this largely contribute to the internal energy of this specific system, I should say that this kind of vibration, which may be for diatomic or the monatomic lattice, basically these are the phonon vibration, as I could say. These are the phonon vibration. So this phonon vibration contribute mostly into this contribution of the specific heat of solid. Now let us start with a very classical theory of this kind of uh, lattice or the specific heat. So first I should say that if those vibrations are independent, because I have considered initially the classical theory. So I should have to consider that these vibrations are basically independent, and I can also say that the atom or the molecules, they have continuous energy level. So the energy is continuous. And according to classical theory, the energy of any harmonic oscillator, that is basically P square by twice m plus some potential energy. P is the momentum divided by twice m plus some kind of potential energy is there. Now this potential is basically plus half m omega 0 square x square. So this is basically the amount of potential energy that are present for any simple harmonic oscillator. So as this energy is contributing the specific heat, so I should have to calculate for a large number of system the average energy of the molecular assembly or the atomic assembly. Now as we know here that the number of atomic oscillator that are present at any particular temperature, this number is governed by Maxwell-Boltzmann distribution. I should apply the Maxwell-Boltzmann distribution to calculate this average energy. Now, number of harmonic oscillator that are basically present between the energy E 2E plus dE is basically exponential minus E divided by K. Okay, so these are the number of atomic oscillator that are present in the energy level E2E plus dE. Now, as I know the energy for any harmonic oscillator is this, so I have to put this factor here and calculate the average energy applying the distribution function. So this is basically the distribution function. Now I have to apply this distribution function to calculate the energy or the average energy of the system. So average energy of this harmonic oscillator is basically sum over n equal to 0 up to infinity. So E dn divided by sum over 0 to infinity dn. So this dn is the number of atomic oscillator that are present at any energy difference E to E plus dE. So this dE basically minus E by kT, right? So as this is a continuous distribution, so I can remove this summation and put some integration here. So this distribution ultimately becomes sum over n equal to 0 to infinity. So E is here. So p square divided by twice m plus half m omega 0 square x square. And in place of dn, I have to write exponential minus of p square by twice m plus half m omega 0 square x square divided by kt. And below this, I have to write sum over 0 to infinity, that is n equal to 0 to infinity, exponential minus p square by twice m plus half m omega 0 square x square divided by kt. So these are basically the expression. So here is a minus sign. So these are basically the expression for contribution, expression of average energy, that is the internal energy of this system. Now if you calculate this, you can apply the sum for this particular thing, and you have to remove this integration, remove this summation and put some integration here, as I have to integrate over px because I use this one-dimensional system, and I have to integrate over x. Now what should I say? This will be p square divided by twice m plus half m omega 0 square x square, right, into exponential minus, so here is p square by twice m plus half m omega 0 square x square divided by kt. Below this, integration 0 to infinity, so exponential minus of p square by twice m plus half m omega 0 square x square divided by kt here. So this is basically the integration of this particular factor. Now I have to remove this momentum part and this coordinate part in a different integration. And I can, if I remove this term, so exponential p square divided by 2m kt plus exponential 1 by 2 kt m omega 0 square x square, I can just divide this two part here. Now I can write this whole thing as integration. Now as x runs from just 0 to infinity, but this px, this can runs from minus infinity to plus infinity. So when I put some integration here, I have to use the integration from minus infinity to plus infinity. So this runs from minus infinity to plus infinity. So minus infinity to plus infinity. Now put here p square by twice m and exponential, just momentum term comes here. So minus, right, and I use the integration here as dpx dx, here also dpx dx. Now it is divided by integration minus infinity to plus infinity exponential minus p square by twice m kt dpx, here also dpx, plus another factor comes here in terms of this x. So integration minus infinity to plus infinity, x also runs from minus infinity to plus infinity, so half m omega 0 square x square into exponential minus m omega 0 square x square m omega 0 square x square by 2 kt divided by minus infinity to plus infinity exponential minus m omega 0 square x square by 2 kt into dx. Here also some kind of dx here. Now I get two integrations. One is for this momentum, another is for this coordinate. And for as the system is continuous, so I have to remove this summation and put some integration here. Now if we use two standard integral, what are those standard integral here? You have already learned this thing in classical mechanics. So without going into the further detail about this integration, I have to say about this two integration here. One is if you put from 0 to infinity, this will be exponential minus alpha u square du. This will be half of pi by 2 to the power half. So this is one standard integral, and another standard integral is if you put u square exponential minus alpha u square du, this will be 1/4 of pi by alpha cube to the power half. So this is integration number 1, this is integration number 2. If you put this two integral, use this two integral here, for this you have to choose this integral, for this you have to apply this integral. In the similar way, for this you have to apply this integral, and for this calculation of this you have to apply this integral. If you put this integral, you can see that the term which I get from this particular whole thing is basically half kt, where k is the Boltzmann constant, and from this particular part I get the term of kbt. So this whole thing is equal to only just kt. So the values of this average energy per degrees of freedom is basically equal to kt according to classical theory, right? Now if this E equals to kt, what will be the value of this specific heat? So there are, if there exists n number of atoms there, so energy for all those n number of atoms, this becomes basically so internal energy is basically there are n number of atoms in one dimension, so there are 3n number of atoms in 3 dimension basically. So 3 into n times this k into t, right? So internal energy is basically 3n kt. Now the specific heat Cv is basically del u by del t when V is constant, and this will be 3nk equal to 3r. So this derivation is basically Dulong-Petits law. And as Dulong-Petits law says about the specific heat of solid is basically equal to 3r. So this 3r is basically independent of temperature, because all the temperature, I can say that the specific heat of solid remain as constant. But this is not true when I have to consider the lower temperature, because at lower temperature the system undergoes a small amount of vibration, because the vibration becomes smaller, so it must affect on this specific heat. And the experimental curve that which is presented or which is derived by different scientists, those experimental curve does not match with this Dulong-Petits law at lower temperature. It uh, it defines or it explains the specific heat of solid at higher temperature, very it is a nice representation. But when we consider the low temperature, the things become completely different. And as the things become completely different, I have to explain that particular temperature, and there must be some kind of fault in derivation of this Dulong-Petits law or its application. So what are that particular fault is explained by Albert Einstein. And what Albert Einstein assumed that basically the discrepancy of this specific heat or derived by Dulong-Petits law is carefully explained by Einstein on 1906. And Einstein assumed that the simple harmonic oscillator are independent. The simple harmonic oscillator, they does not provide any continuous energy, because if you consider the Planck's law, it defines that the radiation or the interaction between the radiation and the matter is basically the discrete energy levels of the air. So as there exists a discrete energy level, so Einstein assumed that the atoms which I am going to use for contribution of specific heat, they are not to basically produce any kind of continuous energy, but their vibration are independent of each other. This proposition remains there. And each atom, they are vibrating with a single natural frequency. Okay, so first, this vibration is independent. Second, this vibration is not produce any, not continuous energy levels are there. So there exist discrete energy levels, and each atom are vibrating with a single natural frequency. So these three are basically propositions of Einstein, and as you see there, the discrete value means the atom have, of course, about energy either h nu, 2h nu, 3h nu, and in general in h nu. So this proposition is not mentioned in case of Dulong-Petits law. Now, as we learn here in the system, any quantum system that undergoes to a very small amount of small temperature, so this system must have kind of 0 point energy, and that 0 point energy is basically half h cross omega, right? So the energy of any quantum oscillator, quantum harmonic oscillator, that is basically E equal to n plus half of basically h cross omega 0, because the system is vibrating to its natural frequency. So in place of classical energy, I have to use this quantum energy to derive the specific heat here. Now, if this is the quantum energy, now I have to use this quantum energy to calculate this kind of specific heat, and at the same time I have to consider the system is not practically classical, it is basically the quantum or the discrete system. Now the average value of energy this must this must governed by the Maxwell-Boltzmann distribution. So the average energy is basically sum over 0 to infinity here n plus half, because n equals to 0. So h cross omega energy, and exponential minus 1 upon kt n plus half h cross omega 0, right, divided by sum over n equals to 0 to infinity exponential minus 1 by kt n plus half h cross omega 0. So this is basically the average energy of the system if we consider the system having the discrete energy level of this amount. Now, in place of h cross omega divided by kt, I have to use the term x. So, in this case, h cross omega divided by kt, assume that this equals to x. So the term becomes n equal to 0 to infinity. H cross omega I bring out, so half exponential minus n plus half x, and below this sum over n equal to 0 to infinity exponential minus n plus half into x. Now I have to expand this whole term. What should I get? This is h cross omega 0. So if you put n equal to 0 here, so this will be half of exponential n equal to 0, so half x. So x by 2, right? Now plus 3 by 2. In place of exponential, I have to use this e to the power minus x by 2 here. So e to the power minus 3 by 2x plus 5 by 2 e to the power minus 5 by 2x plus etc. Below this, what should I get? This is e to the power minus, here I have to consider that this x by 2 plus 3 by 2 e to the power minus 3x by 2 plus 5 by 2 e to the power minus 5x by 2 plus etc. Right? Now, if you differentiate this term here, I can write that if you remove this all coefficient here, I can write the term which is above. The whole thing is basically h cross omega 0 d by dx of logarithmic of this term. So e to the power minus x by 2 plus e to the power minus 3x by 2 e to the power minus 5x by 2 dot this. So this is basically the expression. Now if you bring this e to the power x by 2 out, so what you will get? Will get that this is h cross omega 0 d upon dx log of e to the power minus x by 2 into, again here exists some other term, so logarithmic of 1 plus e to the power minus x plus e to the power minus 2x plus dot. This is an infinite series, right? So what is there? Here is plus here. So h cross omega 0. So log e to the power x by 2, this gives me just minus half, right? So this will be just here minus of plus. If you use this summation here, you will get plus of log 1 minus e to the power minus x, right? So as you see here, if you so this will be just half of x. So if you differentiate this term, what you will get? Minus half plus differentiation of this term. So I can see here e to the power minus x divided by 1 minus e to the power minus x is here, right? So I have to use this term e to the power x minus 1, right? So this is basically the average energy of this particular system, and in place of x I have to write just h cross omega divided by omega 0 divided by kt. Now this is the average energy of this particular system. Now the total energy, total internal energy, this is U equal to 3n of this E. So this equals to 3n h cross omega 0 minus half plus 1 upon e to the power h cross omega divided by kt minus 1. Right? So this is basically the energy of this particular system. Okay. Now if you calculate the specific heat CV, so CV equal to del U by del T. So you see here, if you differentiate this particular term, this remain constant, so this will gives me 0, as this is independent of temperature. And for this term, what I will get, so I have to get from this term as 3 in h cross omega is here, so another h cross omega comes out, and this kt, so this will be h cross omega, this is omega 0, so h cross omega 0 by kt square. Right? Times exponential h cross omega 0 by kt divided by e to the power h cross omega 0 by kt minus 1 its whole square. So this is basically the specific heat CV at any particular temperature. So this is the expression here. Now if you choose this h cross omega 0 by k as Einstein temperature, this is theta E. So CV becomes 3n theta E divided by T its whole square exponential, so theta E divided by T divided by e to the power theta E by T minus 1 its whole square. Right? So this is basically the expression of specific heat at any particular temperature. Now I have to analyze whether this particular expression can explain the fallacy, the problem of associated with this Dulong-Petits Law. So at high temperature, Means when this T is very greater than theta E, if this T is very greater than theta E, this e to the power theta E divided by T, this term becomes smaller. So as this term becomes smaller, you have to expand the whole term, and with respect to this one, you can neglect this complete term here. So this CV at becomes just 3 in K here. If you put some particular thing here, you see that this CV becomes 3 in K. Now this is basically equal to 3R, which is quite which explain the Dulong-Petits Law very fine. Now at low temperature, when this T is much less than theta E, what happens? CV equals to, so I cannot, this term becomes higher because T is much less than theta E. So I can neglect this one in case of this, neglect one with respect to theta E. So 3 in theta E divided by T square into e to the power theta E by T above and e to the power theta E by T square at below. So this becomes e to the power minus theta E divided by T. So at low temperature, the specific heat of solid never becomes equal to 3R, but it is something different, 3 in theta E divided by T square exponential minus theta E by T. Now if you draw the curve, what happens in case of Einstein formula? If you draw the curve between, so this is basically CV, this is temperature. At higher temperature, this curve shows a asymptotic behavior with respect to 3R. But when the temperature becomes low, the curve becomes tends to 0, and this becomes approximately 0 at lower temperature. Einstein says that there is a fall of specific heat at lower temperature, but there exists some kind of problem in Einstein theory, because experimentally it has been proved that this falling nature of this curve at lower temperature is much faster than what Einstein proposed. So this falling nature becomes much faster. So this falling nature is like this. Okay, so this curve is explained by Einstein, but experimentally this is the curve. So there exists some kind of problem in Einstein calculation of this Einstein specific heat, though this calculation fairly explain the nature of the specific heat of solid at lower temperature, because it at the first time Einstein proposed that there must be some kind of fall of specific heat at lower temperature. Okay,